Can you hear me? Awesome. So thanks for having me. My name is Nick Miller. I'm actually going to be talking on a subject kind of related to tilers. Instead of WebSockets, I'm going to be talking about webhooks. So this is a recent project that a couple of devs and I worked on, which is a framework that uses the AWS Software Development Kit and serverless architecture to handle large influxes of webhook traffic. So this is called Nami. It was built using Node.js, and we published it as an npm package for easy installation. So here's a couple of topics that I was going to talk to you about. First, going to go into a little background on what webhooks are and event-driven architecture, and then what Nami is and what specific problems it solves, and then kind of look step by step into how I developed it and some challenges and optimizations. And this isn't everything that there is to know about it, so if you guys are interested in learning more, feel free to talk to me afterwards. So what are webhooks? So webhooks are user-defined HTTP callbacks. It's kind of a dense phrase, so I just want to unpack that with an example. So let's say somebody bought something on an online store, causing a credit card transaction to happen on Stripe. If you're not familiar with Stripe, they're a popular online payment processing service. Stripe makes a post request to a URL endpoint that's provided by the online store, and then sends all the information regarding that transaction event in the body of the request. So then the endpoint receives the request, it sends back a status 200 response indicating that it was successfully received, and now the store knows that this transaction happened, and it's got all the relevant event information. It can go ahead and ship whatever was sold. So this is kind of like a real-time notification that was facilitated by webhooks that allows that online store to initiate a workflow to ship the product. So things people used before webhooks, so API polling was pretty common. Polling is a request-driven model, so it means the client initiates a request for data, and then a server responds to that request synchronously. So polling, a client would poll a server with HTTP requests at specific time intervals, see if there's any updated information, and it's only really after an event occurs that the server has something to send back. So this actually creates a lot of unnecessary load on those systems because the client here has to make a lot of requests that don't really result in a lot of data, and the server's got to respond to all those requests even when there's not data to send. So webhooks kind of turn that around into like a don't call us, we'll call it you type of thing. So with webhooks, HTTP requests are only fired off when an event occurs. It's an efficient way to transmit data because you don't have to continuously pull for it. And even though it's still using the HTTP request response cycle, it actually decouples the producer and consumer in important ways, and it facilitates an event-driven architecture. So here's a normal request-driven request response cycle. It's got a few important qualities, like it's synchronous, so the client sends a request to the server for some information. It needs to wait for the server to process it and respond back before it can continue execution. It's also request-driven, so the client's making requests of pull information rather than having it being pushed to it. And in this case, the response matters. So the response from the server includes information that the client needs to continue its own execution. So webhooks, we're moving away from this synchronous request-driven model towards an event-driven one, which responds to events as they happen. So first we need to update some terminology. So like client and server aren't really relevant in that kind of a model. So we can refer to those entities as the event producer and the event consumer. So the event-driven architecture model is asynchronous. The producer here doesn't have to wait for the data to be processed. Once it kicks off and sends the event, it can go ahead and just continue on with whatever it's doing. It's also event-driven. So now our event data is being pushed to the consumer only when an event actually occurs. And the response here is only for acknowledgement. So there's no actual data being kicked back. It's just saying that, yeah, I got it. So the asynchronicity and real-time updates comes at a cost. The trade-off you make with an event-driven pattern like webhooks is you sacrifice control of the flow of data. Events just kind of happen as they happen. So when you get batches of events, then it might spawn thousands of webhook-based HTTP requests all at once if each event kicks off an individual webhook. So this kind of traffic pattern can threaten to overwhelm consumers with a massive rate of data. So did an analysis of two different companies experiencing bursty webhook traffic and using a system similar to Nami to consume them. Jira is the company that creates issue tracking software for development teams. You guys have probably heard of them before, maybe. Their system generates webhooks when issues are updated, So if a user updates a huge batch of issues or deletes a huge batch of issues, then a huge traffic spike is created as webhooks are generated for each update. Next with Rewind. So Rewind is a company that uses webhooks to make real-time backups of Shopify users' store data. So if a user updates or if they upload a new catalog of products, then massive amounts of traffic is created when a webhook is generated for each product change. So based on articles from each company's engineering teams, both Jira and Rewind experience traffic spikes roughly 5,000 requests a second, and that's right around the level that the Nami framework is developed to support. So this is the first problem. Webhooks are great. They enable this cool event-driven architecture where your systems are more decoupled than with the normal request-driven one. But the problem is you can't control the flow of data. So the webhook consumer can't tell the webhook producer to slow down if it's being overwhelmed with requests. It just has to kind of match the flow that's being sent to it. So how do you handle this bursty webhook traffic? So the standard solution is to deploy a cluster of always-on servers. So let's say you made some estimates about your normal demands, and you've determined a server cluster size of X should be able to do the job. So it's happily handling all the incoming traffic until it's hit with this burst of webhooks. So there's no way to scale your servers instantly to handle this kind of burst of traffic. So this infrastructure leaves a lot to be desired since it can't really handle varying load. So how do you make this better? A lot more servers, right? It sounds obvious. So you purchase some hardware, you extend your backend code, and then you deploy the additional infrastructure. And nothing can topple this up, right? You're ready. Once that burst of requests happens, you're ready for it. But there's something interesting to note here. Anything below that dotted line, but above the colored line of the graph here, that's all idle time. So a lot of these resources are being underutilized in this case. So fortunately for us, there's a solution to this problem, and they're called Lambda functions. So Lambda functions are AWS's function as a service, or FOSS platform. So FOSS is a platform that allows you to run code without having to manage your own servers. You can just upload your code to the platform, and then the FOSS provider will do everything in terms of managing resources and provisioning them. And most importantly, horizontal scaling is completely managed by the provider. So Lambdas are great because they can scale, but how and when does that scaling happen? For that, we need to understand a little bit about how the Lambda platform operates. So Lambdas are triggered by events. On the back of an event, the platform initializes a container on demand to execute a function. Once the function executes, the container stays alive for a period of time, and then it eventually gets retired. And a single container can handle sequential executions, kind of like in this graph here. So there's no scaling happening here yet. But if you get a few hundred requests coming in over a short period of time, then the container on the last slide can execute some, but not all of the functions initialized by these events. So this is where the scaling happens. The Lambda platform spins up additional containers to handle all of the events. So now you can dynamically scale the compute resources using this Lambda platform. So the system can manage resources elastically. There's no server to manage, and you're actually only charged for the execution time of the code. So Lambda is taking care of handling this bursty webhook traffic problem for us, but of course Lambdas alone don't make a system. So what you need is a system that can take event data from when it's generated all the way to when it's stored or being distributed. So how about this? This is what the Nami framework deploys. It's a pipeline of serverless components. It's got an API gateway, a couple of Lambda functions, some message brokers, and a data store. These components were selected to take into account separation of concerns, fault tolerance, and scaling. So how do you stand something like this up? Well, if you wanted to stand it up programmatically using the AWS CLI or SDK, you need to make over 50 API calls. So imagine having to run this set of commands every time you want to handle bursty webhook traffic. So that's the problem we'll want to tackle. And that's what Nami does. So Nami was implemented to stand up a system to handle webhooks to scale bundling functionality into one command. So you don't need to make a ton of API calls. You see each component being deployed, and then in a few seconds you get a URL endpoint that you can configure with your webhook provider. So I want to talk about how this architecture was built and some of the design choices. So here's just a quick breakdown of components. There's not a lot of them, but there's a lot happening between them. So first is the core piece of the architecture, the Lambda functions. So these were chosen for the auto-scaling power, and they're ephemeral nature, so there's no idling resources. Execution logic within these lambdas was kept at a minimum to enable a quick response back to the webhook provider. All they do is they push a payload onto a queue, and they return a 200 status response. So we have all this event data coming in. Perhaps we want to throw it into a data store. So once the data is in the data store, the user can retrieve it and do whatever they want with it. So it chose a MongoDB NoSQL database because a document database is a good fit for nested JSON structure of event data. Also want the schema flexibility of a NoSQL database, since we should be able to handle webhooks coming in from any provider or for any event. And the MongoDB is deployed on an EC2 instance, which is AWS's virtual machine offering. It's done by automatically passing in a bash script to the SDK call used to create the instance. The database is deployed with Docker as opposed to a direct installation. And one caveat about the EC2 instances is they only have ephemeral instance storage by default. So if that instance ever stops and restarts, all your data's gone. So that's no good. So we attached an EBS volume or an elastic block store, which is their disk storage offering for EC2. So there's a few significant problems introduced here. With thousands of requests coming in at any given second, we run the risk of overwhelming the number of available connections to the data store on the instance. So we need to slow down the flow of data so we don't overwhelm the downstream resources. And we could have provisioned a larger instance size to accommodate more connections, but you still have this problem of tight coupling, right? If the EC2 instance goes down, you lose your webhook data. So we need to introduce some fault tolerance as well. And we want to work with this event-driven data model rather than against it. So if we hold the connection with the webhook producer open while we open the connection to the database, process that payload, write it to the database, and then respond to the producer, you're kind of undermining this asynchronous consumer concept. So what we really need is for that Lambda to fire and forget the webhook payload. So to address those issues, we insert a queue in between the Lambda layer and the data store. So the queue acts as a message broker. It routes queues and delivers messages. It's optimized for high concurrency and throughput, so it scales well. And it does several things for the architecture. It slows down the flow of data by buffering messages until the consumer is able to receive them. It introduces fault tolerance in the case of failure. And it really embraces the asynchronous event-driven nature of the webhook handling system by decoupling the message producer and the message consumer. So the producer doesn't have to know anything about the consumer and what it's doing with the data, and the consumer doesn't have to know anything about the producer. It just has to rely on the fact that these messages are coming out of this queue. So now that the producer and consumer are decoupled, they can go ahead and scale independently. So the queue is an integral part of the system, but the trade-off is additional infrastructure complexity, and it also introduces some new questions. So how do we get the messages from the queue to the data store? What happens if we want to clean up the payload before we put it in the database? And how do we send any kind of event data to external systems? So the answer to this is another Lambda layer that acts as the message consumer for the queue. So the Lambda can open a connection to MongoDB, and it can perform any processing necessary in the payload before sticking it in the database. And it can also allow users to send data to external systems. But we also introduced a new challenge, because before we chose Lambdas because they have this really cool awesome auto-scaling ability, but we really don't want that for this one, because if you just auto-scale indefinitely, then you're going to run into this overwhelming downstream resources problem again. And you also don't want to fight that first Lambda for concurrent executions, because there's a limit. So we set the maximum number of concurrent executions to 5, which is just enough for this Lambda to pull messages off the queue and write them to the database at a throttle rate. We also want to be intentional with the error handling for the message consumer. So in the event of an unprocessable message or extended EC2 downtime, the message can't be delivered. So we don't want to lose that message. So we set up and configured a dead letter queue that is a place for unprocessable messages to come to rest for later analysis and processing. So finally, let's create an entry point to the infrastructure where webhook data comes in, which is the API gateway. So webhook HTTP requests require a publicly available URL endpoint. Lambda function doesn't provide that by itself, so we need an API gateway that can publish it, so it can be registered with the webhook provider. The endpoint is configured to both the webhook receiving Lambda when it's visited And if the user deploys multiple instances of this framework, then all of them are consolidated under one host using different paths. So remember when I said you need to make over 50 API calls to stand up a system like this? Well, with all these different pieces that we're kind of talking about, you get the sense of how big a task this is to do manually. So it's a big job to do even once, but if you wanted to use this framework, or if you want to use this kind of a system for multiple webhook providers, you get a sense of like how much of a pain that can be. So this is specifically the problem that Nami solves. It abstracts away a lot of the complexities of cloud infrastructure by deploying a system with one command. Again, you can see kind of the deploy sequence, and then it'll deploy each piece of the pipeline, and then output a creative endpoint for the developer to use. Right? There. So during development, ran into a couple of challenges and built in some optimizations that I wanted to talk about. So the first one is reusing database connections for the message consumer Lambda that's pulling the messages off the queue. So when a Lambda container spins up, it has an execution context at the container level that all the functions executed within that container can access. So we declared a variable within that context and set it to a database connection. So any Lambda functions that are executed within that container can go ahead and use that existing database connection. And if it doesn't exist, then it'll go ahead and create it and assign it to the variable. And that helps us both kind of reduce the overall execution time for the Lambda functions, and it also helps us better manage the open connections for the database. Second one was there's a challenge with timing when deploying or destroying services in rapid succession on AWS, especially if one service depends on another. So AWS returns optimistic responses. So if you tell it to create something or destroy something, it doesn't mean that that change is propagated across their whole system. So if the next thing that you create or destroy is reliant on that previous call that you just made, sometimes it can error out because that change has not been fully made. So to overcome this, we included some basic while looping that's going to ping AWS for the status of a resource. In this instance, we need to make sure an EC2 instance is fully stopped before we're able to delete an associated security group. So thanks for your time, guys. That's me. I built this project with a couple of engineers in Austin and London, and this is how you can get in touch. The link on the bottom goes to a white paper that kind of talks about things in more detail than I was able to get into tonight. And I'm also currently on the job market, so if anyone is interested in talk about that, I'd be interested too. Thank you.